Loop-mediated isothermal amplification, or LAMP, is gaining a lot of traction in the last years, especially during the COVID-19 pandemic. With its ability for rapid amplification of DNA without the need for expensive, sophisticated equipment, it holds great potential for point-of-need diagnostics and might offer a real alternative to the current gold standard of PCR. In this video, I'll explain what LAMP is, where it came from, how it works, and some of its main features, as well as specific examples of how LAMP is used today. I will mark the different topics in the timeline so you can also just skip ahead. If you're new to the channel, this is my very first explained video, so if you feel that this content is somehow helpful to you, please like and subscribe to my channel. It would mean a lot to me. So, let's get started. Loop-mediated isothermal amplification, or short LAMP, is a non-PCR based method of amplification of nucleic acids. And LAMP is actually only one of several methods which are collectively referred to as isothermal amplification techniques. And the name isothermal amplification actually perfectly describes what these methods are all about. The word isothermal consists of the word iso, which derives from Greek, means something like equal, and thermal, also from Greek, meaning heat, here referring to temperature. So isothermal amplification effectively translates to amplification of nucleic acids at an equal temperature, meaning at the same or a constant temperature. Unlike polymerase chain reaction, PCR, that requires cycles at different temperatures for the amplification process, in isothermal amplification, this process can be done at one fixed temperature, so without the need for thermal cycling. As mentioned before, LAMP is only one of many isothermal amplification techniques, and if we take a look at this graph here from a publication by Beatriz Oliveira et al., we can see that there are actually quite a lot of different isothermal amplification methods out there. What we can also see is that the different techniques operate at very different temperatures, which of course can become very interesting for different types of applications. But let's focus on LAMP, since I guess this is why you clicked on this video, and rightly so. So let me give you a reason why in 2024 LAMP is actually really interesting. So when we search databases like PubMed for publications that contain the term loop-mediated isothermal amplification, then we get over 5,000 hits of publications that contain or at least mention this method. And we can also see that the number of publications since 2000, when the method was first described, has steadily increased until the last years. As you might have noticed, LAMP is in fact not a very new technique. The first publication of LAMP was published by Notomi et al. Already in the year 2000 while working at Icon Chemical Corporation in Japan. Fun fact, Icon still produces LAMP reagents to this day, and when we have a quick look at their website, it turns out that Tsugunori Notomi, excuse my pronunciation, the first author of the LAMP publication, is currently also the CEO of the company. So having brilliant ideas seems to pay off sometimes. So LAMP has been around for quite some time now, but it feels a bit like only in recent years researchers really started to pick up on it. Looking at the underlying mechanism of LAMP, we might first of all ask, how does nucleic acid amplification at a constant temperature actually work? It works because in LAMP we make use of a polymerase that has an inherent strand displacement capability. What does that mean? It means that the enzyme that is performing the amplification reaction can open double-stranded DNA by itself and does not rely on heat alone, like in PCR for denaturation of the double strand and annealing of primers. So at the heart of every LAMP reaction is a polymerase with a strand displacement activity, which is a crucial difference to PCR-based methods. So what else is needed for a successful LAMP reaction? Like in PCR, in LAMP we also need primers to initiate the specific amplification reaction of our target DNA. Unlike PCR, in LAMP we typically have 4 to 6 different primers. We can organize these in 3 different groups: in outer primers, inner primers, and loop primers. Outer and inner primers make up the core of primers needed for a successful LAMP reaction. Loop primers are optional, but can substantially accelerate the amplification reaction if needed. There are 2 outer primers, F3 and B3. F indicates the forward orientation of the primer and B indicates the backward or reverse orientation of the primer for binding the other strand of the DNA template, which follows the same principle as in conventional PCR. The inner primers consist also of 2 primers, the forward inner primer, or short FIB, and the backward inner primer, or short BIB. What is special about the inner primers is that they each contain 2 distinct regions for binding. For the forward inner primer, this is the F2 region at the 3' end and the F1C region at the 5' end. We will later find out why this is essential for the LAMP reaction. Like before, we also have the backward inner primer, which respectively contains a B2 region at the 3' end and a B1C region at the 5' end. And lastly, we have the loop primers, typically a loop forward primer and also a loop backward primer. If we now arrange our primers on a DNA template, it looks like this, with the forward inner and outer primers binding one strand from 3' to 5' direction, and the backward inner and outer primer binding to the opposite strand, also in 3' to 5' direction. What becomes visible now is that the F2 region of the forward inner primer is complementary to the F2C region of the template DNA, and that the F1C region of the forward inner primer is actually identical to the F1C region on the template sequence. And therefore we do not see any binding for that region to the template DNA, but what will later become important for the loop formation during the LAMP reaction. Okay, so now that we know all of our primers, let's walk through the actual LAMP reaction. To make things easier, let's assume we want to use LAMP to identify a virus X in our samples. The primers we designed specifically bind target regions on the genome of virus X. So to initiate our LAMP reaction, we have to apply constant temperature, remember isothermal, typically something over 60 degrees Celsius or 140 Fahrenheit. And this would create the conditions for our polymerase to do its job and for annealing of the primers to the template DNA. Initially, the 3' region of the forward inner primer anneals to the partially denatured template DNA of our virus X and is then elongated by the DNA polymerase. In a second step, the forward outer primer F3 binds to the same single strand of the template DNA, which is located upstream of the binding region of the forward inner primer, which is then also elongated by the polymerase. This allows now for the 5' part of the forward inner primer, the F1C region, that wasn't binding anything before, to bind to the F1 region on the same single-stranded amplicon that was just produced. This leads to the formation of a loop structure, which is also called 5' terminal loop. And now all that needs to happen is for the same reaction to initiate from the opposite direction. So analogous to the previous reaction steps, the backward inner primer anneals, is elongated by the polymerase, and then also displaced by the elongation of the backward outer primer, which is in this example labeled R3. This way we end up with what's called a stem loop, a dumbbell-like structure with terminal loops on either end that is the typical reaction intermediate for LAMP. The stem loop is what forms the basis for further annealing of inner primers and also loop primers, leading to an exponential amplification of our target DNA template. Unlike in PCR, this exponential amplification leads to the formation of different sized amplicons. Ultimately, these amplicons can then be made visible, allowing us to get a result for the presence or absence of our virus X in our samples. Similar to PCR, we can do this using techniques like gel electrophoresis or fluorescence-based detection, either with probes or intercalating dyes. But we can also make LAMP products visible in colorimetric assays or lateral flow assays, which is really neat and I will talk more about in the last part of the video. Okay, so after all of that, you could actually ask, why does any of this actually matter? We have PCR, right? Which works perfectly fine and is used almost universally in labs around the world. Why do we need a LAMP? Not requiring thermal cycling like in PCR is in fact a big deal and unlocks some really powerful possibilities. For one, typical thermal cyclers require a lot of energy as they have to quickly heat up and cool down to perform the PCR reaction, usually requiring at least 2 or 3 different types of working temperatures for annealing and denaturation. Also, thermal cyclers are fairly sophisticated equipment and such quality doesn't come cheap, especially in real-time cyclers. Also, these need some amount of regular maintenance. In contrast, as we only need to heat up to one specific temperature in LAMP, we don't need a lot of energy to do that. And the devices that can do this are typically much smaller, less expensive, and can be operated on a battery for a long time. But there are also other advantages in LAMP. In many cases, LAMP achieves very good sensitivities which are comparable to PCR. Some publications even describe detection limits as low as 1 copy of DNA per microliter. At the same time, because at least 4 unique primers are used in a LAMP reaction, it is considered a highly specific method. Runtimes of LAMP reactions are usually below an hour, while at the same time they generate large amounts of amplification product. Another nice feature of LAMP is that it's relatively tolerant to inhibitory substances compared to PCR. Inhibitors can be a problem in nucleic acid amplification and in diagnostic assays and are frequently present in specific types of samples, for example in stool or environmental samples. But to me, one of the coolest features about LAMP is that the results can actually be read out with the naked eye, meaning we don't need any reading devices at all. The products of LAMP reactions can be made visible, for example, on lateral flow assays, similar to the antigen tests we all know from the COVID-19 pandemic. Or, for example, through a color change of the reaction medium, here shown from pink to yellow. With all these phenomenal features, LAMP can be a great alternative to PCR, especially in situations when access to well-equipped laboratories and PCR cyclers is not available. This could become relevant, for example, after natural disasters, which often destroy critical infrastructures such as power lines, roads, buildings, and also sewage systems. This is also the time when people are hurt and lose their homes, rendering them highly vulnerable, especially to infectious diseases. Fast, reliable diagnostics to monitor the health of people in such situations and to be able to make accurate diagnoses to treat patients is extremely important. Non-PCR based methods such as LAMP could be a great tool to fill the gap, as they are cheap and can deploy in the field or in small mobile laboratories while being powered on batteries and can provide sensitive results in a short time. To this day, LAMP has successfully been used for the detection of different pathogens such as influenza, Zika virus, SARS-CoV-2, as well as drug-resistant bacteria like Staphylococcus aureus and Mycobacterium tuberculosis. But LAMP has not only been used for the detection of infectious diseases, but also in the diagnostics of cancers, as well as monitoring of food safety and aquatic environments. And in the last years, also the first commercial LAMP-based tests have entered the market, for example, for the detection of COVID-19, malaria, and tuberculosis. PCR remains the current gold standard in molecular analysis and amplification of nucleic acids. In contrast, LAMP is a non-PCR based isothermal amplification technique that allows highly specific and sensitive amplification of nucleic acids at a constant temperature. Due to the fact that LAMP does not require thermal cycling, LAMP has great potential to be a cheap, reliable, and fast alternative to PCR, especially for point-of-need testing. I know the mechanism of LAMP can be a bit hard at first to wrap your head around, but I hope this video helped you to get a bit of a clearer understanding of the method and also explain some of the key features of LAMP to you. With that, I'd love to hear what you think about LAMP. Do you agree, and do you see a great potential, or do you think this technology is not quite there yet? Also, to any lab scientists out there that have used LAMP before, I would love to hear more about your experiences in the comments. If you enjoyed this video, again, please leave a like and subscribe to my channel. Thank you. Take care.